Hi everyone. Today let's learn about the second law of thermodynamics. In the previous video we looked at the first law of thermodynamics. So second law of thermodynamics is not a single statement like the first law. So it can be defined using three different statements. We will look at each of these statements one by one. The first statement is the entropy statement. Before moving on, let's learn what entropy means. Entropy simply means disorder. So, higher the disorder, more will be the entropy value. Lower the disorderness, less will be the entropy value. So, the entropy statement says that the total entropy or the disorderness of an isolated system always increases over time for natural processes. So let's tell an example. So you are going to sit on a table to study, right? So you have your books, pen, paper, laptop, iPad, all are kept in their own place. But once you start to study, you will start picking them up from everywhere, right? And once it was ordered, now it's all disordered. That is what second law states. That disorderness of a system will keep on increasing over the time. We will see another example. Consider that it's a very hot day and you have taken a few ice cubes. So this ice cube has a well-defined structure, right? They are highly ordered. So that means their entropy is very low because they are ordered, they are happy, they are sitting there. And what will happen? Eventually, it will start absorbing the heat from the surrounding and it will start to melt. When ice melts, it will become water. Water has molecules which can move around very freely, right? So what happens? The entropy will become higher for water molecules because now it's free to move anywhere. The randomness has increased for the ice. So here the heat transfer is spontaneous. We are not putting any work or we are not putting any effort. It's naturally occurring. So when the heat transfer is happening, naturally occurring, the entropy increases in the system and the surroundings, right? So this is what the second law states. Now let's consider the reversible process. In a cold country, what happens? The water will freeze, right? And it will become ice. So in this scenario, if we think, okay, water is disordered, its entropy is high, but when it freezes, it becomes ice. That means the entropy is decreasing. According to second law, it should happen the other way, right? It cannot be happening in a reversible manner. But here also, in the case of freezing as well, the entropy, overall entropy is increasing. I'll tell you how. When water freezes and turns into ice, it is a exothermic process. That means while the water is freezing, it releases heat to its surrounding. So what happened? The entropy of the surrounding increases. Even though the entropy of the system is decreasing, the entropy of the surrounding is increasing. So the total entropy, the overall entropy is still increasing. So it is again validating our second law of thermodynamics, which is the total entropy of an isolated system always increases over time for natural processes. So this is the entropy statement. Now let us look at the Kelvin-Planck statement. So Kelvin-Planck statement tells that no heat engine can convert heat into work with 100% efficiency. Some energy is always lost as waste heat. So let me tell you an example to make it a bit more realistic. Consider that you have a Ferrari or a Porsche or any car of your liking. That would be great, right? In an ideal scenario, what do you want? When you put a fuel in, you want the fuel to use all the energy to move your Ferrari as fast as possible, right? So you don't want to waste any fuel. You want to use all the 100% energy to be used as for working the car, for moving the car as fast as you can. But in real life, unfortunately, what happens when you drive a car very fast? Part of it goes into motion, moving your car. And what happens? The rest of it is lost as heat. That is why when you come out of your car after a long trip and you keep your hand on the top of the car, it will be very hot, right? So next time when you think your car is hot or you burned your hand, you have to blame the second law of thermodynamics, right? Because it is just wasting your fuel as heat. So here also you can see that the second law of thermodynamics applies, because the energy is converted or the fuel is converted to do work, motion, and released as heat. When heat is released to the surrounding, what happens? It changes the surrounding and it increases the entropy of the surrounding. So, to summarize, Kelvin-Planck statement tells that no heat engine can convert heat into work with 100% efficiency. So, energy is always lost as waste heat. So, this is the second statement which you can use to define second law of thermodynamics. Because ultimately, it is also telling that some energy is lost. That means the entropy of the system has changed and it has released heat to the surrounding, increasing the total entropy of the system plus surrounding. The next one is the Clausius statement. Clausius statement tells that heat always flows from a hotter body to a colder body. In simple terms, you can say that. Or if you want to make it a bit more, complicated, and for the exam you have to write it, you can tell that it is impossible for heat to flow from a colder body to a hotter body without external work being done. So, for example, you have kept something in the freezer. It's a hot body, right? You have to transfer cold or heat from the colder body to the hotter body. In that case, we have to put electricity. We are using a refrigerator. That is external work. Naturally, if you take, it is always that hotter body will transfer heat to the colder body. Let's take an example. Consider that you have pouring a hot coffee or hot water into a cold mug. What will happen? The mug will warm up while the coffee cools down, right? So, the coffee is transferring or the hot water is transferring the heat to the cold mug. And the energy will spread out evenly. It will spread out to the surroundings as well. Here, the coffee is losing heat, reducing its entropy. The entropy of the coffee is becoming less because it's losing heat, and what is happening? It is becoming more ordered. On the other hand, the surrounding air is getting or gaining more heat. So, the particles start to move around very drastically, causing more disorderness, which will cause an increase in entropy. Simple, right? So, to conclude, a Clausius statement tells that it is impossible for heat to flow from a colder body to hotter body unless you apply external work. Thank you for watching. Hope you learned something new today. Bye.